Gabby is here. Vanessa is here. Sarah?
Yeah, exactly. So I was like, well, I think
Gwen? Melanie? Karen? 3, 4, 5, 6. Okay. Good morning, Victoria. We're signing on to GSS 93 this morning inside of SPSS, so that if you are on a terminal that's not working, why don't you just move to one that is. Good morning, Jake. We haven't started yet, Jake, but we're getting everybody onto a terminal that works and can get into GSS 93. We're going to be doing hands-on all day today.
There was even one where I was like, I never took concept, but I'm pretty sure I can figure this one out. So, yeah, I know. I told you, the first question was like, what's the difference between major depressive disorder and bipolar disorder? I was like, okay.
Good morning, Hannah. I know we haven't started yet, but we're just getting everybody onto SPSS. We're going to get into the GSS 93, and when we get started in a moment or two, we'll be hands-on all day in multiple regression. If your terminal isn't working, please move to a working terminal. Okay, we've got 8:30, so why don't we get started? Good morning, Psych Stats.
Good morning.
Welcome to Wednesday. Looking forward to today's session. I wanted to congratulate you all on another effective journal club. I appreciate the conversation that we had the other day. You also got some feedback this morning from me on your journal club responses in TED-Ed. We'll have another TED-Ed coming up for an upcoming session, our next session, and we'll be soon making our way to t-test, but we have some work to finish in multiple regression. A little while back, we had a very interesting TED-Ed session on multiple regression, and we laid down some theory, and we had different kinds of multiple regression techniques. In fact, there were 3 of them. So just to review a little bit, can somebody remind us of the 3 different styles of multiple regression that we talked about? 3 different procedures that we might use. Yell them out if you recall them. Stepwise is one of them, okay? Hierarchical and simultaneous, and a synonym for simultaneous is the standard, okay? So you can also cheat by looking at your handout there, right? Okay, the answers to those questions were highlighted there in red, okay? Can somebody just remind us briefly how maybe stepwise compares to hierarchical multiple regression? How are they similar? How are they different? Maybe how they're different is most important. Stepwise versus hierarchical. Okay, thanks, Hannah.
For hierarchical, you put the variables in order according to a theory that you're testing, and stepwise, the computer does it for you. Okay,
right. All right, so we have the hierarchical approach, which is maybe we have some kind of theory that either we've created or somebody else has created, and that specifies what goes into the model first. Remember that we talked a lot about how order of entry matters. And what we're doing in multiple regression is really quite sophisticated. This is something that many undergraduates never get to in a psychology course. It's something that is akin to factorial ANOVA that we're going to be doing next week. But it is something that most undergraduates don't get to. And the reason is because there isn't just one answer. The answer that you get depends very much on what kind of model that you use, what kind of multiple regression model. And if we have our order of entry considerations. Then we can think about how we'll have a theory that will specify what comes first, second, or third. In a stepwise, as Hannah correctly mentioned, the computer makes the decision. Can somebody remind us, how does the computer make the decision in a stepwise analysis? Yeah, Quinn's got it.
We'll do it based off of what is their significant.
Okay, what is most significant gets in first, right? That's the first step, so to speak, and that could be any one of them. So it's almost as if the computer considers them all for a moment equally, and then asks which one is the best predictor, okay? And the criteria actually is just a little bit more refined than that. That's the first step, and the very first question is the best predictor a statistically significant predictor? And if it isn't, we just stop there and we don't have anything in our model. That is to say that there is no prediction whatsoever from the model. If there is a significant prediction, after the first one makes it in, then the next question is, do we get a statistically significant improvement when we add whatever variable is second? And if the answer to that is yes, then we'll add that one, and we'll get a change in r squared. Who remembers talking about the change in r squared, as opposed to just regular r squared? Okay? And then we proceed through all the different possible variables, and we stop as soon as we get to a variable that doesn't contribute anything significantly to the existing model. Okay? And all lower order variables would then also be out of the model in a stepwise case. Okay? Can somebody give us a reminder about how the simultaneous or standard case was different from those two? Okay, thanks, Gary.
It considers all variables at once, and it considers which variables account for variance that isn't explained by any other variable.
Right. What variance is explained uniquely, if you will, by any one variable that's setting aside or controlling for all the other variables. Okay, so now we have at least those three. There are other kinds of MRs, but that would keep us busy, certainly for today. Okay, so what I thought we'd do today is get some practice. Now we have some idea about the theory behind these things. There are a couple of other ideas that I want to return to that are sort of theory related. These are the notions of partial and semi-partial correlations. Also something that will be important for tomorrow's PowerPoint, the 1022 PowerPoint, something called collinearity or multicollinearity, a concept we haven't talked about there. But as we get into today's hands-on session, I wanted to just point out that we'll take a look at some of those features, collinearity, multicollinearity, and also part and partial. But why don't we just see if we can get the correlations going first, the correlations boxes, the multiple regressions, three different ways. Okay, so we're going to use our GSS 93. How many people have GSS 93 up and ready to go? Okay, all hands are there. Okay, so why don't we see if we can move ahead. And what we're going to try to do is just talk it through at first, and then we'll build these different models. So if you'll join me into the variable view, I'll click into variable view, and then we'll look at the different variables that we have here. You might remember that we have a huge number of people in this GSS 93 set. We have 96 variables. I've got my eye on variable number 10. This is the educational variable, or one of a few different educational variables. And you can see that this pertains to the highest year of school completed for this particular respondent. Okay? So we'll have that actually for all of our respondents. That's what we're going to try to predict. Okay? And that's going to be our criterion variable. And we can use any number of predictor variables. Because it's multiple regression, we have to have at least two. What I'd like us to use today is variables 12 through 15. So this will be your father's highest degree, your mother's highest degree, the sex of the respondent, and the race of the respondent. Okay? Now, it's not necessarily the case that everybody's going to have all that data for a given participant. It might be that the mother's degree is missing. Maybe there is no father or no mother, or maybe we don't have that information. But we will use predictors 12, 13, 14, and 15. Okay? And what we're trying to predict, our criterion variable, is again number 10. So we're predicting number 10 based on 12 through 15. Who's following that? Okay. Now there are simpler and more complicated multiple regressions, but we'll get the ball rolling just with this. Okay? So what I have for you is a handout that I just cooked up this morning, and I wish I had made this in earlier years. But just to walk you through, you'll see something like this. And for any kind of regression, we're going to always start out in SPSS by clicking on Analyze. Right? That's very common for almost all of our analyses. We'll do a regression in linear. You've done that before. Even when we did the simple bivariate case. Who remembers doing that for the bivariate case? Okay, so that much is pretty much the same. And also we're going to slide in the criterion variable. which is our outcome variable, our dependent variable, just like we did in the bivariate case. Okay? And then we'll have some decisions to make depending on whether we'll do stepwise, standard, or hierarchical. Why don't we do all three today, and we'll get some practice building our regression equations, both z-score style and raw score style. Okay? So we're going to do really three different equations because we have three different MRs, and we'll do that for standardized and for unstandardized tests. Okay? So you can hang on to this. I'll flip over to here, and we'll see if we can get this going. All right? So you tell me what's my first click. What did we just say? Analyze. Okay? And if we're going to do a multiple regression, then we want to click on regression. Okay? And we're going to click on, here's regression. Which one? Linear, okay. And remember that we did nonlinear regression, but we're doing linear regression this time around, and it's going to be multiple. So let's open that up, and we'll see how many people get this box. Is that working for us? Okay. All right. So what we want to do is use as our dependent variable, our outcome variable, our criterion variable, the respondent's highest year of school completed, and that's variable 10. So how many times do we click downward? 9. Okay. So also, if it helps, here's a little trick, because we'll probably have this on a SPSS quiz. The box pops open at a certain width. If you grab it on the right-hand side and you bring your cursor over to the right-hand margin of that, you can expand it, and then you get a better look at the variable names. People see that? So you can expand or collapse. It doesn't change the computation in any way, but it makes things easier to see. So here I am. I'm going to dial down 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I get highest year of school completed. I'll slide that over and make sure that everybody's with us. Is that working? Yep? Okay. All right. Now we have a couple of different ways to go here. We are deciding that we want to do stepwise first. Okay? So I'm going to call your attention to where this is. You might have noticed this on the PowerPoint that I asked you to read for today. We did not have a TED Ed for today, but I did ask you to look to a PowerPoint. And here's where things get a little hairy. Okay? We're going to put all of our predictor variables in the independent box. Not too surprising. We did that in the bivariate case. But we have different kinds of methods. And here, where it says method, I'm going to ask you to dial down with me to one of the options, and it's called stepwise. Couldn't be simpler. Okay, so we have stepwise. Okay, and it was Hannah who told us a moment ago how that will work with respect to order of entry. And we want to add, now in our stepwise multiple regression, these 4 predictor variables. Okay, and they were variables 12 through 15. So that's going to be father's degree, mother's degree, sex, and race. So I'm going to dial down, and you can join me in doing that. There's father's degree. And I'm holding down the shift key, and I'm clicking on these 4. You can move them over individually, or you can hold down the shift key, select them, and then slide them over. So we have father's degree, mother's degree, respondent sex, and race as our predictor variables in our stepwise regression. Who's got that? Is that working for us? Okay. Okay, so far so good. There are so many things we can do. It would be very easy to get lost in multiple regression. So many different options that we have over here. It's mind-boggling. I have to confess, I don't know all of the possible options, and there are so many pairwise combinations. But why don't we open up statistics and take a look at just a couple of the options? Okay? And I'll check in with everybody. How many people have the statistics box open? Is that working for us? Okay. So far, so good. Okay, it seems to default to getting regression coefficient estimates. And that's really the whole point of doing multiple regression. Right? We want to build these equations, so that will always be there. Model fit. Why don't we take at least the first 4 on the right-hand side? Why don't we take the r-squared change, so we can see after something has gotten into the model, what does the next variable do for us incrementally? Right, the change in r-squared is what that's going to buy us. We'll get some descriptive statistics. For each of our variables, we'll get some kind of indicator of central tendency and dispersion. Why don't we take part and partials? We were introduced to that in our last session when we discussed this. Okay, we're going to leave out collinearity diagnostics for now. We might come back to that. We actually get something about collinearity in the output anyway. Okay, and we can take confidence intervals, I suppose. Okay? They might not bias that much. For right now, we're going to leave out residuals. There's a lot to be said about residuals when we begin to analyze the assumptions that underlie multiple regression. We haven't spent a lot of time on that yet. I'd like to come back to that throughout the semester and also see how the assumptions that underlie multiple regression are identical to those in many ways that underlie Anova and t-tests. Okay? So right now we have these 4 and these 2. Who's okay with that? Okay? All right, we'll click that away. Okay, and I think we're ready to go. So we'll click on OK. Okay, and in just a moment, the output comes up. How many people are getting output? Okay. All right. Why don't we take it box by box? And what you might walk away from this conversation with is the idea that some of these boxes, I think, are much more informative than others. We'll take a quick look at each of them, and then we'll see which ones we really want to focus on. So here's the descriptives. Right? Highest year of school completed is what we're trying to predict. And you can see that the mean for this particular sample, remember this was taken in 1993, was about 13 years. So on average, through 1 year of college, everybody in this room has done more than that, interestingly. Okay, and then here you have your other variables. You can see that they're coded differently. Right? So they're going to have some kind of other way of counting the number of years completed for your mother's degree and your father's degree and so forth. Okay, I'm going to now point our attention to the correlations box. This is one of three. We get a bunch of boxes. This is one of three that's generally a keeper in my estimation. We typically do want to have this. These give us what we call the zero-order correlations. And that's a term I'm not sure we had used before. When we say zero-order correlation, we mean just a simple bivariate correlation between any pair of variables that we would have. Okay, so if you had these data in in Excel and you used equals Carrel or equals Pearson, this is the correlation that you would get. Okay, we actually haven't looked, I think, at a correlations box like this yet this semester. So I wonder if somebody can walk us through what's going on here in this box that says Pearson correlation. We know it's a Pearson correlation, but can you just tell us how this is all laid out? And why is it the case that we have ones down that primary diagonal? Okay, Karen's got that, yeah. Okay, right. So here we've got, highest year of school completed with highest year of school completed, father's degree with father's degree. Is that clear to everybody? And people follow? Okay. You may have seen that in some other classes. You might not have. How many people had seen that before? That kind of a layout. Okay. Sometimes what happens, by the way, is that in these, sometimes in a journal article, they will give you this, and they'll just take out the bottom portion underneath the diagonal. Let's take that out. Why would they do that? Why would they remove everything here underneath that primary diagonal? Yeah.
Because it's repetitive. It has like the same combinations of pairs.
Exactly, right? So on the one hand, you could say, what is the correlation between A and B? Or you could say, what's B and A? And for correlations, those don't matter. But for regression, that does matter, as you might recall, right? Okay. All right, so far, that looks like the group is on track with that. It is interesting to just scan it and see what's doing some predicting here and what is not. We're getting really quite modest predictions and associations when we look at highest year of school completed and something like the respondent sex and something like race of respondent. Those are very, very close to zero. Okay? By the way, what would it mean to say that we have a negative correlation for respondent sex? I mean, respondent sex is, presumably male-female, right? It's a pretty modest correlation. It's almost zero, right? But it still came up slightly negative. So how would you get from something like male and female to a negative correlation? How would that work? Yeah. Okay, thank you. Right, I wanted everybody to think very deeply about how things are coded, and we'll take a moment on that. Okay, because what we have to do for multiple regression, we've said it before, but I haven't said it this morning, is that for the criterion variable, it has to be continuous or something like scale. We might be cheating a little bit here. It might have been coded as an ordinal variable inside of SPSS, but we're going to pretend it's a continuous variable. So we are assuming that we can compute means on our dependent variable on the y-axis. Okay? The predictor variables themselves can also be continuous, but they can be dichotomous, or they can be really any type of variable. And so if we go with, say, one gender is number 1, another gender is number 2. Those are dummy numbers, but they can be used quantitatively, right? And we can say as you go from 1 to 2, the trend is coming downward. That would be a negative correlation. As you go from 1 to 2, the trend is going upward. Okay? As you go from male to female, it might be going upward or downward. Who's following that? Okay, so we're using dummy coding for this dichotomous variable, and that can be true for any number of variables. Now, we can move these variables around, but we actually couldn't use a multiple regression to predict, if you will, the respondent's sex, okay, because that's going to be not a continuous variable. Okay? There is a type of regression called logistic regression, which we haven't done yet, and we will do later on, where you can use something like a multiple regression format to make predictions about dichotomous variables. Is my patient in this category, or is my patient in that category? And a lot of times clinicians will want to be able to do that. Okay? But for right now, what we're doing is trying to predict something on a continuous scale, and we're assuming that highest year of school completed is more or less continuous. Okay? Who's following all that? Is that working for us? Okay, so we have the correlations. Okay, variables entered or removed. Now, we've done here a stepwise comparison. So what we see is that when the computer looked at all the possibilities, as Hannah mentioned correctly a little while ago, it looks like mother's highest degree entered first, father's highest degree entered second. What happened to the other two variables? Yeah, thanks.
They didn't account for a significant amount of variance, so they weren't included.
Yeah, they didn't make the cut, right? They didn't make the cut. And again, what we can say is they actually might be significant predictors. Maybe they're not. Actually, when we take a peek up here, it looks like they're really not significant predictors. They could have been. The question really becomes, after the very first one is entered in stepwise, is there a statistically significant increment? Is the change in R going to be statistically significant? We okay with that? Yeah, okay, really good. Okay, here's another one that I think is very important. I actually think variables removed is pretty unimportant. You can kind of figure all that out by other information, but there it is, okay? Here's one that I think is another keeper. There are actually going to be a lot of boxes. I think 3 are keepers. Everything else could probably go. The second box that I think is a keeper is the model summary box, okay? So this basically tells us what Hannah had alluded to. The first time through, one of the variables made it in, and it gave us an R of 0.417. Okay, a little bit confused. Well, here's R squared, so you can just square that and you get that. This is the proportion of variance explained. Okay, and this is telling you, this R will tell you how good the model is doing in its entirety at any given step along the way. Okay, so here on step 1, we're at 0.417. We square that. We're accounting for 17% of the variability in your highest year of school completed can be predicted by your mother's educational attainment. Who's following all that? Okay. Here's something that's a little bit interesting, maybe a little bit confusing to some students. There is the R squared computed straight up, and then what happens is SPSS does something called an adjusted R squared. And this is a finer point, okay, but the notion is this. Almost always we're working with a sample. And samples, particularly when they're small, might be a little bit misrepresentative of the overall population. So based on how big your sample is, SPSS will make an adjustment to your R squared and say, well, if you have a really small sample, you probably haven't really explained as much of the variability as you would like in your overall population. So we're going to tax you just a little bit. We're going to shrink down your R squared by some amount that is proportional to how small your sample size is. Who's following that? Does that work for us? And the actual computation need not concern us, and there's some debate about how that should be computed, but SPSS is making an estimate. Notice that these two numbers are really quite similar, and that's because we've got a pretty good sized sample, right? The GSS 93 was over 1,500 folks, and way up top, I think we have more than 1,000 people in our analysis, okay? So these two numbers are going to be pretty similar to each other, okay? All right. Standard error of the estimate is also in the model summary. Anybody want to guess what that is all about? Standard error of the estimate. It's conceptually similar to something we've done previously, but we haven't talked about this one directly. It's very similar to something we've earlier done. No? Okay. So here's the idea. We're doing regression. Regression is all about prediction. So far, so good? Okay. You can imagine that we're going to have dots all over a scatter plot, and we're going to have a best-fitting regression line that's going to be consistent with the form y equals mx plus b, but now we have a lot of m's. Right? We have lots of slopes associated with each of our different predictors, and in this kind of regression, they're all going to be linear predictors, so it's going to be a simple scaling factor. We go up by some coefficient or down by some coefficient. Right? Okay. There's going to be some margin of error. If you can imagine that I've got my dots all over the place, and I'm fitting the best line, we might ask, on average, what's the extent to which we are off in our predictions? Okay? It's kind of like when you're listening on election night to the returns for the election, and we'll say, well, in this particular state, candidate X is winning, and the score is 45% to 38% with a margin of error of 2 percentage points. Has anybody ever heard that announcement? This is kind of like, what's the margin of error associated with your prediction? Okay, and that's very much like having a standard error bar on your means, right? So when you're creating a t-test plot, you'll say, first mean was this high, second mean was this high, and we put those error bars on there. Okay, now we're essentially putting error bars on our prediction line. Okay? And this would suggest that we're going to have some standard error for our estimate that's going to be 2.768. So we might be off by something like 2 years on our number of years completed. Okay? Who's following that? That works for us? Okay. Now here's the change in R squared. So first time through, we went from 0 up to 17%. Here we get some information about the equivalent ANOVA. There's a mathematical equivalency between a regression and an ANOVA. They are both linear models, okay? And we can leave the significance out for right now. Then later on, the model finds out that we can add another variable. This turned out to be the father's degree, and we went from explaining from an R value of 0.417 to 0.457. We added about 3 percentage points, maybe a little bit more than 3 percentage points in variance explained. Okay, and now we've also sharpened our standard error by just a little bit. Right, we've shrunk the error bar down just a tad. So by adding that, we can get a slightly better prediction. Okay? And it turns out to be a statistically significant improvement and so forth. Okay, so I think this is a really nice keeper. It tells you how the model is changing as variables are coming in. So we like the correlations box. Okay, we don't like the variables entered. In fact, I'm going to get rid of that. You can join me in clicking on that and getting rid of it. Okay. Here's an ANOVA, kind of interesting. It's not going to be a keeper. Again, you can see that we can run a full ANOVA on this data set with the very first model, which was mother's degree. Okay? And then the second model is going to be the combination of mother's degree and father's degree. Okay? And as I mentioned a moment ago, there's a formal mathematical similarity between ANOVA and regression. They're both linear models. We'll develop an intuition about that on Friday when we're talking about t-tests. Okay? But this doesn't really tell us that much. I guess you could pick up something like mean squares if you wanted to report that, but for me, it's not a keeper. We're going to try to be parsimonious about all this. Okay? This next box I love. I think it's maybe the most important of all of them, coefficients. We are here to predict. Right? That's what multiple regression is. Regression is synonymous with prediction. And if we want to build these equations, then we're going to need to pull the information out of our coefficients, just as we had done once before. And the reason that we have different boxes here, going across in these rows, is they're showing you the coefficients at different points in the stepwise regression. So if you only had the mother's highest degree predicting, these would be the coefficients that you would use. If you now add fathers, things change around a bit, and we have to reconfigure our coefficients. Okay, we have the standardized and unstandardized coefficients over here. Who's following all that? Yeah, is that working for us? Okay, excluded variables. That will be our last one, and we will wind up excluding this box, but just to walk it through, in the very first step, the one that made it in was mother's degree. Therefore, the 3 that were excluded are these 3. Okay? On the second step, the father's degree made it in too, so the 2 that were excluded are these. People following that? So we kind of figured that out already by seeing what was in the model summary and seeing what was in the correlation. So I think this is largely redundant. So what I'd like to leave you with is this formula for how we're going to be working with multiple regression. A simple acronym that I'd like you to remember is CMC. Those are the 3 boxes that I think will matter. Okay, we want the correlation so we can see 0 order, just what's correlated with what. Forgetting about the complications of order of entry. Okay, the model summary, we can see how this thing is being built. Okay, and this time we are using stepwise. And then the coefficients will be what we need to actually build either a raw score or a z-score regression equation. Okay? I think that's the most parsimonious way of thinking about this. Okay? One other thing I'd like you to do, can you join me by going up top to here where it says regression? And we're going to label each of our regression models. This one was stepwise. So if you click on the word regression, and then I think you might have to double-click it also, and a flashing cursor becomes available to you. I'm going to put in dash stepwise. Because what will happen is, in a few minutes, we'll add another one after that, and we'll begin to have lots of different kinds of regression models, and we want to clearly label them so as we're scrolling through, maybe on a quiz, it's really clear to you that if you want the stepwise coefficients, you want to be in this area. Okay? All right, any questions so far? Okay, so why don't we use the stepwise model, and why don't we have you tell me how to build a regression equation using stepwise, and we'll go ahead with this one. This is our full model from stepwise, okay? So I'm going to be over here, okay? And can somebody tell me how I should lay out my y equals mx plus b? We'll use the unstandardized coefficients first. Okay? So, you tell me. Somebody want to walk me through? I'll give you y. How about that? And what does y correspond to, by the way? What variable are we predicting? Look at your output. Education? Okay, right. So the education level. Right. Put that down here just to remind us. But we're looking at y. Okay. Anybody want to go ahead and walk me through? Is that a hand? Yeah. Oh, that wasn't okay. Okay. We've done this before using bivariate regression, so really the same kind of thing. Right? I'm trying to predict y or education. Okay, thanks.
Is it the 12.1?
Okay, that's going to be our constant. That's going to be y equals mx plus b is going to be our constant is going to be this 12.165. Right? That's going to be our constant. Why don't we start out with that? 12.165 plus, okay. Well, actually, you know what? It could be that. Why don't we stay down here with the full model? Okay, so we'll use this one. That is a constant for the very first model, but we got a better model over here. It's going to be 11.964. Okay, why don't we use that one? .964. Okay. Then what happens? We still have a plus. And people are not sure. Okay. All right. I wasn't sure if this was too. Sometimes when there's no response, we're on the ceiling. Like, you got to be kidding us. You're asking such an easy question. Sometimes we're on the floor. Okay. What we're going to do here is we're going to grab this one, the unstandardized coefficient, 0.94, and we're going to use that as our multiplier for the mother's highest degree. So we have 11.964 plus 0.94 times, that's the coefficient of the mother's degree variable. I'll call that MODEG, I think is how they abbreviated that. Okay, can somebody tell me about the next one? What's going to be the next term in our model? 0.573 times PODEG. And normally we would have the plus b over here, but we just started out with it because SPSS tends to give us the constant first. So either of these would be fine. You could have the education level is equal to this plus this and that, okay? And the MODEG is accounting for a little more. We can do the same thing over here for stepwise, but we'll now use the z, okay? These are the standardized coefficients, okay? So we can say that zy, we're trying to predict the z-score for the education variable, is equal to, and we'll pick up here 0.29, okay? 29 times the z-score of MODEG, it's your mother's degree, plus 0.227, hopefully people see this as a standardized coefficient, 0.227. Times the z-score for PODEG. And notice that there isn't an intercept. What's the deal with that? Somebody want to remind us? So typically over here we had an intercept. We had a constant. That's our intercept. Right? What's the deal with nothing showing up here? Yeah, thanks.
For z-score, the minus of the 0.
It's always 0 definitionally, okay? So this thing always starts at 0. So it's a little bit simpler that way. So if you happen to have the z-score coordinates for mother's degree and father's degree, you could predict the education, and this would be a significant predictor. And according to Stepwise, you could add other variables, but it wouldn't really buy you anything significantly. Okay? How do people follow that? Is that working for us? Okay. All right. Okay. So what we have then is a z-score prediction. We have a raw score prediction. We have our 3 output boxes, CMC. We have the simple correlations. Okay, you did that kind of a thing even in Psych 200. You might have done some of that in Psych 100. We get the model summary. It shows us how this thing is being built according to the stepwise procedure. And then we get the coefficients. Okay. All right, while I have a moment, maybe what I'll do is just point to something that we had seen before. Here are the zero-order correlations. Right? This is really simple. Right? We know zero order would just be what we get for a simple Pearson or equals Carrel inside of Excel. Part and partial is what we have here. This is the partial correlation. This is the semi-partial correlation. Who remembers hearing about that from the other day? The semi-partial correlation, okay? Can somebody remind us, why is it the case that the semi-partial, 0.188, is smaller than the partial? Does anybody recall why that's the case? Okay, yeah.
There's something in the Venn diagram where like the overlap is smaller.
Yeah, right. Okay, so the idea is we might ask here, what is the covariation or the correlation between the predictors and the criterion after we remove all other variables, right? And then over here, what we're going to say is, what is the contribution from this variable to the overall level of variability inside of the criterion? And sometimes a picture will say 1,000 words for us. So Gabby was correctly recalling, and I think we can get, it'll take me a moment to figure out where this was. Part and partial, it was not in 1021. It might have been in 1014. It was toward the end of 1014. And we have these Pac-Man looking like things. Okay, let's call this up. Okay, who remembers seeing this? Does that look familiar? Okay, so he was correct in going. So here's a zero order, right? That's just a straight up correlation. And then we can now remove some other variability from the criterion variable and also from the predictor variable. And when we remove it from both of those components, we call that a partial. And then if we leave the criterion variable in its entirety and ask what is the unique contribution of this variable to that in its entirety, then we get the semi-partial. And what you can see is here we have a certain amount of overlap. It looks like it's the same. That black area is a larger fraction of this fragmented disk than it is to the disk in its entirety. People seeing that? So it's going to be a smaller portion here for the semi-partial. Slightly confusingly, SPSS calls the semi-partial the part. Okay, so let me flip back over. Here we are in SPSS output. Okay. So zero order partial, this would be semi-partial, it's called part. Okay, and it is smaller, and you'll see that on a regular basis. It was true even in this other variable here. All right, people seeing how to interpret all that? Hopefully you see a connection between that Venn diagram and what's going on here. Okay, so far we've done a fairly thorough analysis in our stepwise comparison. In the time that we have left, what I'd like to do is, why don't we try two other varieties? Why don't we see if we can take a look at what's next on your sheet, and that's going to be a standard or simultaneous MR, okay? Unless there are questions. And we'll do the simultaneous or standard MR, and we'll generate the same three outputs. We'll get a whole bunch of them, but then we'll whittle it down to the correlations, the model summary, and the coefficients box. We'll always go with these three. Okay? Okay, can you remind me, how do we get this analysis going? We're going to do a standard multiple regression. We're going to click on what? Analyze, okay, and then what? All right, we're doing well, and now what? All right, you can see how that's pretty straightforward, but there would be a lot of places to make an error if you were new to this, okay? Why don't we leave the variables just as they are, but we're going to change this now to simultaneous, right? So what you would hope from SPSS is if you just change the method, same variables, different regression method, if you clicked on this, you would hope that you could scroll up and down and you would find something called either simultaneous or standard. Okay, that's what you would hope. That's not what you see, though, okay? What you see is nothing labeled that way. We're going to go back to enter. Okay? We go back to enter. And now I'm going to call your attention to something that I hadn't highlighted previously. You may or may not have noticed previously that all of these variables, these independent variables, and the method are existing inside of a larger box that's called block 1. Okay? When we did the stepwise, we only had one block. And here we're only going to have one block. In a little while, we'll return to this and we'll do the hierarchical model. And we'll have multiple blocks, where in block 1 we enter the first item in our hierarchy, right, in our theories hierarchy, then the second item. And you can just keep on going and going. I don't know how many blocks this thing allows you, but typically it defaults to just one block. And we're going to throw all of them in now simultaneously rather than in a stepwise manner. And so the way that we do that, I wish they had called it simultaneous. They call it enter. Sorry about that. Okay, so we're going to leave it as enter, and that's on your handout. Right, so hopefully your handout, just to point out where that is, we're on its second or third block. This is the method box at enter, okay, and we're going to have all of the predictor variables in, and there's only one block. It's block 1 of 1. Okay? Okay, now this might produce the same kind of output or different kinds of output. Why don't we see how this compares to the stepwise bit? We'll leave everything else the same. We'll click on OK. We'll let it rip. Okay? And we get another regression block of output. How many people got something there? Okay, before we go any further, can you join me now and click on the word regression? How are we going to label this one? The last one was stepwise. This one will be called standard or simultaneous, right? It's the same variables. Okay. And so the descriptives haven't changed at all. Really, the correlations would not have changed at all either. If you'll join me just by clicking on the descriptives, why don't we get rid of that? We'll always try to have CMC in our output, at least for this class. I think that'll be plenty for us. We won't need variables removed, but we'll come back to that in just a little bit. Okay. We want the model summary, so we can see how things are changing. And there's only one line there. That's pretty interesting. Anova, we can get rid of that. Doesn't provide anything new. Coefficients, there they are. Okay. All right. So let's take a look at what's going on here. I'll let you take a look at any of this output, think it through, and then we'll see if somebody can help me build our equations. Notice that we have only one line here. Why do we have only one line here in our model summary? So, yeah, thanks.
Since everything was entered at once, there's only one model.
Yeah, so it's really obvious if you think about this not being a standard model, but a simultaneous model. Right? There's only one step, okay? And what we're going to see here are the coefficients that talk about the unique contributions that these things are going to be making, okay? Okay, so at the risk of being redundant, but it is good for us to get some practice, we're going to try to predict y one more time, which is our education variable, okay? And on this board, we're doing the raw score equation. Can you help me out? How will I get this going? Somebody yell out, what's my first number to enter? Okay, that's going to be our very first coefficient, right? We can start out that way. If you'll bear with me, we'll also put our constant first, okay? But that was a perfectly reasonable way to start. So Shelby was right on that. 12.427. Plus what Shelby said, and Shelby said 0.573 times, and that turns out to be father's degree, PODEG, plus, you tell me, what's next? 0.932 MODEG. I think you get this, plus, actually you can actually leave it as a minus. Minus 0.07 responding to 6. Okay, so a really small effect there, and probably non-significant. So the times 6. And then we also have a minus 0.293. And that's going to be race. Okay? So still, generally of the form y equals mx plus b, we have all these different coefficients. Okay? We'll do one more. We'll do the z-scores. Okay? So we're not going to have an intercept, but this is going to be zy. So this is the z-score associated with the participant's education. Highest year of school completed, 0.227, 0.287. And that's times the z-score for MODEG, sorry that this is so small, but this is a fairly long equation, plus 287, I'm sorry, that was PODEG and then MODEG. Plus, okay, a really small fraction there, minus 0.011 times 6. Okay. In fact, I can just leave that as a minus. Okay, and I have one more minus, and that's going to be the race of the respondent, 0.049. I'll make that the z associated with race. I want to make sure all these are clearly labeled as z's. Okay. I think people are following that. So you can see it's a little bit tedious. You have to be on it, and you have to pull out a very precise piece of information from all of this clutter. But I do think it can be helpful to get rid of some of the boxes you don't need and focus either on the standardized coefficients or unstandardized coefficients. Okay, just in the interest of time, we have time for one more. We won't write out the full equation, but I think you would get it. Why don't we do the hierarchical variety? Okay. So you tell me one more time, I realize it's redundant, how will we get the analysis going for our last analysis? Analyze, regression, linear, okay. All variables are going to be the same. Okay, now what we'll do is we're going to leave it at enter. And this, you can look right along here on your cheat sheet. We're going to leave it at enter. Okay, so for the moment, it looks like it's simultaneous, but we're going to take advantage of something else. I'm going to slide out, in fact, why don't we do them in this order? Why don't we just put them in the order in which they appeared in the list? We'll make the father's degree step 1 in our theory. Okay, so this is going to be in block 1. Yeah? People see that? Okay. So we're going to pretend that our theory goes predictor 12, 13, 14, and 15 from our list of predictors. We'll click on next. Okay. And then we'll slide in mother's degree, wherever that went. Okay. So mother is step 2. We'll click on next. Respondent sex just happens to be next in our list, so we'll pretend that we have a theory that's specifying that. Okay, respondent sex goes in there. And then we have a fourth variable, which is the respondent's race. Okay, so I'm still using enter. It's a little bit confusing. We use the word enter both for the simultaneous variety and also for the hierarchical. But in the hierarchical, we start taking advantage of different blocks, and we can sequence them. Okay? And we'll click on OK. And we get this, and we'll just label the last one regression, and we'll call this hierarchical. All right, that's our last bit. We'll get rid of the descriptives. Correlations are by now redundant, but just as a habit, we will keep the CMC going, so we can always see the zero-order correlations. We can see what the model is doing for us. Okay. We can get rid of the Anova. Here are the coefficients. We'll get rid of the excluded variables. Okay. And you can see now we have 4 steps in our model. What to do on the first round, second, third, and fourth, because we told our SPSS analysis that it would have 4 different steps. And you can see it's building up, and you can see the incremental increases for R squared, not always buying us very much. Between the second and third steps, we went up by essentially 0, but it's still in there because we said put it in there. Okay, and SPSS followed our instructions. Okay. I won't go through. We can now make an equation out of this, but I think you get that point. All right, so we've done lots of different analyses here. Okay, we've done stepwise, standard, and hierarchical. Who's okay with all of that? Questions? Well, thank you for your efficiency. Here's some good news, I think. So I don't think it's happened to me before. We're actually where we're supposed to be and a little bit ahead of where we're supposed to be. So because you've been good, I'm going to give you tomorrow off. You don't have to come in tomorrow. Okay? We'll just come back on. We'll just come back on Friday. Okay? Right? Yeah, we could do this again tomorrow, but why don't we just sleep on it? We'll let all this stuff sit in. But here's what I would like you to do. I'm going to have a TED Ed for you on Friday on t-test. We don't want to lose. Why don't we do it this way? We'll have an agreement that you will do for Friday maybe one more multiple regression for me, and I'll have it cooking over here for Friday. Okay, I'll put this out on Blackboard. What I'd like you to do is, same thing that we just did. Can you please run in SPSS 3 different multiple regression analyses, just like you have on your sheet, right? Stepwise, simultaneous, and hierarchical. Can you put as your output CMC? Okay. I won't ask you to write out all the equations. And here's what I'd like you to do. Can you please predict, and this will be on Blackboard, can you please predict, where is it? Here we go. We'll ask you to predict variable number 21. That's the respondent's income. Okay, so that's, if you will, a continuous variable. Can you predict the respondent's income by using 4 predictors just like we did? But now the predictors are going to be age, just for kicks, zodiac sign, okay, right? And the education level, which was our criterion variable a little while ago, and our party ID. Okay, so you're still having 4 predictors. Okay, and what I'd like you to do is save your output to your assignment inbox. And your output will look just like, if you want to save what we just did to your assignment, that's fine. I'll save it. And you're going to have a stepwise variety, CMC. You're going to have a standard variety, CMC. And you're going to have a hierarchical variety, CMC. Okay? And you have all day tomorrow to come in and work on this, all day today to come in and work on this. But you don't have to be here at 8 o'clock tomorrow. You get to sleep in, let all this settle. All right? Thank you for a great session. I look forward to seeing you Friday. I will have a TED Ed for you also, probably by this time tomorrow, ready to go for simple t-tests. So it'll be a lot easier than what we're doing here. Okay? All right. Thanks, everybody. I'll see you on Friday in this context. Sleep in tomorrow. Remember CMC in your output boxes, in your assignment inboxes. Yes, thank you. Thanks, Victoria. Okay, thanks to you.
I know, I can either. Yeah, it is.